Today we are covering lesson 6.5, trigonometric form of a complex number. Now, we have dealt with forms very similar to this in lesson 6.3 when we're talking about vectors. So be aware it's going to look very similar to the trig form of a vector. So absolute value of a complex number is very similar to magnitude of a vector. So what it is given a plus bi, right? Absolute value of that is a squared plus b squared under square root. Okay. Distance away from 0. So if that's the distance away from 0, we will see what that looks like plotted in a moment here. So to plot the points 3 plus 2i, right? We have a real axis and we have an imaginary axis. The real axis is the x-axis, so that's where the a value is going to go. And the imaginary axis is the y, right? We formerly known as y. So this 3 plus 2i is going to be graphed like 3 comma 2, right? So we write 2. Now think about it. How far is that away from 0? It is precisely the form we just showed you, right? If we try to find how far is that away from 0, we've got 2 here, 3 here, and the distance here is the square root of 3 squared plus 2 squared. So that's where that comes from. Plotting the next couple, -4 minus 6i, so 4 to the left, 6 down, 1, 2, 3, 4, 5, 6. So there's where that point would be. The last is 4 minus 2i, would again look like 4 minus 2, 1, 2, 3, 4, down 2, and there's the point. Pretty straightforward. Next, the trigonometric form of a complex number is given z equals a plus bi is given by z equals r times cosine theta plus I sine theta. So what's r? R is that magnitude. And again, what I was referencing earlier, remember when we covered that, let's say a vector was, just for a second, x, y, we could also write it as magnitude cosine theta, comma, magnitude sine theta. This is the exact same thing, just instead of dealing with vectors, we're dealing with complex numbers. So instead of xy, we have ab. And so what do you think is going to happen? Tangent of our angle is going to equal b over a. What is r? R is basically the same thing as magnitude. R equals the absolute value, right? Square root of a squared plus b squared, and a equals r cosine theta, b equals r sine theta. So again, just drawing this for 1 second, let's draw 4 plus 2i. Okay? Sorry, 3i. Because I had no one 3i. Right, there's 4 plus 3i. Right? We can also write this as, right, kind of when we make our angle here. Right? We've got this angle here between the x-axis, or our real axis, and our point, which is going to be given by, if we kind of finish this triangle off, right? We've got a 3, 4, 5 triangle. 5 is going to be what r is, right? The square root of 4 squared plus 3 squared, so it's a Pythagorean triple. We'll just go with that math and say it's 5, right? You can 16 plus 9 is 25, do it that way as well. And our angle equals our y value over our x value, but tangent of our angle equals that. So we're going to tan inverse 3/4 to get our angle. Our tan inverse of 3/4, we're doing a lot of 3, 4, 5 triangles. That is going to be 36.87 degrees, right? So just a heads up, like there would be our theta, and r is up here. So we could make our trig form of what we have up here. Z equals r cosine theta plus I sine of theta. Convert the complex number from standard form to trig form, or vice versa. Okay. So 5 plus 2i, again, this is the point 5, 2. So first thing, let's find r. R equals the square root of 5 squared plus 2 squared. 25 plus 4 is 29. So we've got the square root of 29. Next, we need our angle. Tan inverse of 2 over 5 gives us our angle. So getting out your calculator, make sure you are in degrees in terms of your mode. Move your tan inverse of 2/5, and I get 21.801 degrees. So there's our angle, and now to finish the form, we've got square root of 29. This is how they showed it. Cosine 21.801 degrees plus I sine, again, the y value had the I, sine of 21.801 degrees. And that is that. Next, we can also, a little indifferent, they showed it this way, you can also have the square root of 29 multiplied in, to look like this. I squared root of 29, kind of go backwards, but sine 21.801 degrees. Right? And that as well, less parentheses, a little more writing. Next one, we've got, this one is trig form. We've got r, and here's our theta. So, sounds like a lot of math, just multiply it out. What is cosine of 5 pi 4? Again, 5 pi 4, so just point down here, which is negative 2 over 2 for both values. Yeah, plus minus pi root 2 over 2, multiplied by 8. What do you know? Both of these are going to end up with a 4 left over. So negative 4 root 2 minus 4I root 2, or I 4 root 2. Kind of like 4 in front of the I. And that is that. One more left. Sorry, 2 more left. Negative 7 plus 2I. And this is like the point negative 7, 2. 49 plus 4. That's where I'm at already with my R. Square root of 53. And then for the angle, tan inverse. Now you got to be careful with tan inverse because more often than not, it'll lead us astray. Let's think quick about where negative 7, 2 is. So to determine is this the angle or just a reference angle? Negative 7, 2, like way down here, right? Tan inverse is not going. Right? Tan inverse is here in quadrant 4 and quadrant 1, knowing our domain. So whatever angle it gives us, that's what it's going to give us over here. We're going to add 180 to it. So I'm doing tan inverse of negative 2, 7, or 2 over negative 7. We both recognize that I'm referencing quadrant 2. So we have to add the 180 to it. So I got 15.945 negative. So add 180, and I'll get a little less than 165. 164.0546. It's going to round up. Sorry, I didn't round before when I wrote. So 0.055 degrees. Next one, and now we've got negative 3, negative 4. Sorry, we didn't finish. Ready for the next one. We've got our angle. Took us a little long to get our angle and our R, so we're going to rewrite square root of 53 cosine of that angle. 0.55 plus I square root of 53 sine of that angle. And one last one here, negative 3, negative 4. When you square those, we get 5, right? That one's a pretty, when you get Pythagorean, I don't expect you to show a lot of work. But now we're doing tan inverse of negative 4 over negative 3, which again is going to give us quadrant 1. It's going to give us the angle, just like I had written before, of a 3, 4 triangle. Okay, tan inverse of the 4 over 3. These are going to be that same 36 degrees I had before. Let me check, I might be off here. Tan inverse of 4/3. Sorry, 53. Gives us the complement to it. 53.130. And then we're going to add 180. Because again, negative 4, negative 3 is in quadrant 3. We get 233.13. So 5 cosine of 233.13 plus 5I sine of that same number. And there we are in trig form. Next, how to multiply these. Now we've got the rule is on our formula sheet. We'll still go over it. V1 is R1, right? times cosine of theta 1 plus I sine of theta 1. Z2 has the 2, R2 cosine of theta 2 plus I sine of theta 2. Are complex numbers. Z1, Z2 equals, you're multiplying your R values and adding your arguments or your angles. So angles are added, absolute values are multiplied. If we're dividing, same idea, except for backward, right? Dividing our radius, subtracting our angle. And again, with the note that Z2 cannot be 0. Okay? We couple these problems. So again, now we're multiplying. So here's our R1, R2. We're going to have 3 times 4, 12. Now when we're adding, notice these are fractions. So pi thirds is 2 6 plus 1 6. We're going to have 3 6, which is 1 half. So filling it in, we've got 12. Again, times cosine of pi half plus I sine of pi half. Does say to leave it in trigonometric form. You'll realize this stands for, if I remember off the top of my head, 12i, because the cosine of pi half is 0. So sometimes the simplify is pretty nice and neat, despite being trivial. Next, division. It almost looks, set up like you're supposed to divide. That's how it's going to work. 2 over 4 times, and now we're doing subtraction. 50 minus 40 is 10. And so I'm just going to simplify our way. Half, parentheses, cosine of 10 plus I sine of 10. We can multiply the half and rate and leave it on the outside. Next, now we've got to the 4th power. How is this going to work? Okay. So the 4th power, I just want to think about it for a second, because it's theory as we're going on. We have 4 r's, right? And 4 thetas, right? Times another r, times another r, times another r. And then we're going to have 4 more thetas, too, 3 more thetas. Right? So we're going to have theta plus theta plus theta plus theta, and r times r times r times r, right? 4 times. We're going to end up with, pardon me, r being multiplied by itself 3 other times, so r to the 4th, times cosine, and then it's going to add up 4 times. So 1, 2, 3, 4 theta plus I sine of 4 theta. That's what I'm getting my theory crap. So what can we kind of assume? There's a rule called the Loss theorem, which is z equals r cosine of theta I sine of theta, r times the quantity. And n is a positive integer. We're not talking about square roots or inverses. So z to the n equals back to the n. Where does the n distribute into? As we saw, we have n angles, right? It's multiplied in because we had n of them, and our r on the outside receive the n as a power. So to make it difficult, let's do one where they give us the other 4. So we have 4 and 2, and now we've got n is 5. Let's turn this into trig form first. So 4 squared is 16, 2 squared is 4, square root of 20 is 2 root of 5. We're going to leave it as square root of 20 for now. Okay, because we're going to get it to the 5th power. It's going to get a little messy, right? So let's think about it. What's square root of 20 to the 5th? Okay, well, writing it out in its terms will help us. We've got 4 times 5, so 2 times 2 times 5, and we're going to have 5 sets of these, right? So what are we going to have? We're going to have 5 2s, another 5 2s, 5 5. Okay, so what's coming out, what's not? We're going to have 5 2s come out. We're going to have 2 sets of 5 come out, and 1's still going to be underneath, right? Because these are all under the square root. And remind you. So 2 times 2 times 2 times 2 times 2, we've got 32 times 25. 32 quarters. This is going to give us 800 root 5. 800 root 5. Now we need the angle. So then we're doing tan inverse of 2 4. Fortunately, this is quadrant 1. We don't have to mess with it at all. 2 4 2 is in quadrant 1. So tan inverse of 2 4 is 26.565. And then we're going to multiply this by 5. I'm doing something calculator right now. before I round, and I get 132.825. So angle is 132.825. Again, it gets times by 5, not to the 5th power. So I'm going to run out of space here, but I'll try to squeeze it in. We're just going to go down and run plus I sine of that same value. And that is times 5. Pretty lucky. Homework for tomorrow is right there. It's also posted on Google Classroom.